Good day, ladies and gentlemen. This is our first discussion on physical sciences, grade 10, term 2. We are going to talk a little bit about matter and materials today, specifically covalent and ionic bonding. Now, as you should already know, all matter, all material is made up of atoms. Apologies. Is made up of atoms, electrons, protons, neutrons. Now, atoms are these very small basic units, and they make up everything. Now, you've all probably at this point had a look at a periodic table already, so you should be relatively well versed in what an atom actually is, as well as the different types of atoms. This discussion, as I mentioned, is going to focus on covalent versus ionic bonding. Now, the first thing that one must consider when looking at these bonds is that you have something that is called a diatomic. Diatomic molecule. A diatomic molecule is a molecule that contains two atoms, di being the Latin for two. So something like oxygen, which is O2, is made up of two oxygen atoms, hence diatomic. There are many different elements in the periodic table that like to be diatomic rather than being a single atom by themselves. Oxygen, iodine, phosphorus, bromine, chlorine, nitrogen, just a few. Now, these diatomic molecules form covalent bonds. Now, the diatomic molecules are not the only ones that form covalent bonds. Things like water, H2O, also forms a covalent bond. The definition of a covalent bond is a bond where the electrons are shared between the atoms. So if you were to use H2O as our example, we have an oxygen and we have two hydrogens. So when we say an electron is being shared, we have electron shells, as you will have done in your previous term. You've got your first electron level, your second, your third, and then you've got your s and your sp orbitals and so on. What happens is each of these two atoms wants to have these orbitals filled up completely. Now, just a very simple example, for instance, the s1 orbital can hold two electrons. So right now we have one electron over here and we actually want two. So what happens is one electron from here and one electron from the oxygen gets shared. So this hydrogen, in essence, now has two electrons, one from itself and one sharing with oxygen. Same thing happening on this side. And same thing happening with the oxygen. So covalent bonds are the sharing of these electrons. In covalent bonds, you have something called allotropes. These are chemicals, or compounds rather, that have the same atomic structure. They are made up of the same atoms, but they behave very differently. An example of this would be carbon. Carbon, C, if you arrange the atoms of carbon in a certain way to make rings, you have something like graphite, the tip of your pencil. If you arrange them in a different manner, you've got something like diamond. Obviously, diamonds are very hard, very valuable. Graphite, very soft, it's your pencil, not very valuable. So allotropes are what we call these compounds that can have different properties but are made up of the same atom. This is because of the crystal structure, and we will talk about the crystal structure in a future discussion. Now, covalent bonds have certain properties. They usually are relatively simple compounds, and this means that they usually have relatively low melting and boiling points. This is because the forces keeping the atoms together is not particularly strong, so not a lot of energy is needed to break them, hence the low boiling and low melting point. Covalent networks, these more complicated structures, like diamond for instance, they can have very high melting or boiling points. So if they become complex, they can have a very high melting and boiling point. This depends on the crystal structure. A simple structure, like graphite for instance, versus a complex structure, like diamond. There are no free electrons. This is because the electrons are shared. Now, this is also particularly important because free electrons are what allows a substance to be able to conduct electricity. So because there are no free electrons in something made up of a covalent bond, that means it does not conduct electricity. And now you might say that I spoke about water previously being a covalent bond, and yes, water actually does not conduct electricity. Pure water, chemically pure H2O, is a extraordinarily poor conductor of water. It's all the things that you add to water, like salt for instance, that adds free electrons, which makes it a conductor. Salt water, very good conductor. Pure water, very poor conductor, an isolator. Now, this is pretty much everything about covalent bonds, and apparently also the end of my exam pad. Now, ionic bonds are our next topic of discussion, and ionic bonds differ from covalent bonds in that we do not have electrons being shared. We have an electron being what we call donated. So what would happen in something like sodium chloride? We have the sodium, Na, being positive and the chlorine being negative. Being negative means it has an extra electron. Being positive means it has one fewer electron. So on this side we have minus one electron, and on this side we have one electron extra. So what happens when these two compounds bond, the chlorine essentially hands over one of the electrons to the sodium when they bond. So in an ionic bond, an electron is donated by one of the elements, the other one receives it. This is a very important distinction between covalent and ionic, the sharing of electrons versus donation of electrons. Sodium chloride would be an excellent example of an ionic bond, and water would make a very good example of a covalent bond. Just like covalent bonds, ionic bonds do have certain properties that can be generalized about them. To start with, they tend to be solids at room temperature, and they tend to have very high melting and boiling points. Melting and boiling. This is because they form much stronger bond. Rather than an electron just being shared, you have one being completely donated, so you have a much stronger bond. Stronger bond means more energy is required. More energy required, higher melting point. They are also often called salts. For instance, sodium chloride, we call that a salt generally. And they tend to, in that form crystals, which tend to be very hard as well as brittle. Solid ionic compounds don't conduct electricity very well. Not a good conductor, because again we have no free electrons. When ionic compounds melt, when the ionic compounds melt, then the electrons are free to move around. So what we say is, as a solid, they are not a good conductor. But if you were to dissolve this in water, for instance, then we have now broken down this compound. The electrons are now free. Free electrons means it can carry a charge. So if they were to be dissolved, then it becomes a good conductor. And you will remember that I said a while ago that water in and of itself is a very poor conductor. You add salt to it, salt water, it becomes a very good conductor. Here we now have an ionic bond. When they are solid, they are poor conductors. Salt, you break it up, you dissolve it in water, free electrons, an excellent conductor. Now, these dissolved bits of the ionic bond in water we call electrolytes. You might have heard of electrolytes. In physics, rather than biology, we refer to electrolytes as these dissolved particles that can carry a charge. In biology, they serve a different function in terms of hydration and functioning of your cells. Now, this does bring us to the end of our discussion on covalent versus ionic bonds. From this point forward, we will talk briefly about metallic bonds, and the reason we leave that over for next time is because metallic bonds will form the start of our discussion on crystal lattices and crystal structures, which will be the topic of our next discussion. Until then, ladies and gentlemen, have a good day.